What if, right now, while you're lying in the dark, the oldest light in the universe is still traveling toward you from nearly 13.8 billion years ago, carrying whispers from a time when the cosmos was only 380,000 years old? Most people will scroll past this fact. Most will never pause to imagine that the faint afterglow of the Big Bang, the cosmic microwave background, still bathes the entire sky at just 2.7 degrees above absolute zero. But you're here, and tonight, you're about to drift through the quietest mysteries of existence. Welcome to Velarin, Sleepy Space Mysteries, where science slows down, softens, and gently unfolds in the dark. In this journey, we won't rush through equations or overwhelm you with noise. Instead, we'll float past the first stars that burned 1,000,000 times brighter than our sun, through invisible oceans of dark matter that shape galaxies, and toward a future where even black holes evaporate in unimaginable stretches of time. The universe is vast beyond instinct, hundreds of billions of galaxies, each holding hundreds of billions of stars, arranged in a cosmic web stretching across billions of light years. And yet, somehow you are awake within it. Stay with me. If this thought already makes you feel smaller, calmer, and quietly amazed, then you're exactly where you need to be. Subscribe to Velarin Sleepy Space Mysteries. Like this video, turn on the notification bell, and join our membership to travel deeper into the cosmos with us. And before we drift further, tell me in the comments where you're listening from. I'd love to see how far this signal reaches across our tiny blue world. We begin at a moment of gentle transformation, a quiet turning point in a universe that had already been expanding for 380,000 years. Until this time, space was not dark in the way we imagine night. It was bright, almost blinding, filled with a dense plasma of free protons and electrons moving restlessly in every direction. Photons, particles of light, were everywhere, but they could not travel far. Each time a photon tried to move forward, it collided with a charged particle and scattered. The cosmos was like a glowing fog, luminous yet opaque, a place where light existed but could not truly journey. As expansion continued, the temperature slowly fell. The universe cooled to about 3,000 degrees above absolute zero. That cooling changed everything. Protons and electrons, once too energetic to remain together, finally combined to form neutral hydrogen atoms. This process is often called recombination, though it was the first time these atoms had ever formed. When the charged particles paired up, the fog began to lift. Photons no longer scattered endlessly. They were released, free to travel across space without constant interruption. In that instant, the universe became transparent. Light, which had been trapped since the earliest moments, began its long voyage outward. Those ancient photons are still traveling today. They have crossed billions of light years, stretched and cooled as space itself expanded. What was once brilliant visible radiation has been elongated into microwaves, now measuring just 2.7 degrees above absolute zero. This faint afterglow fills the entire sky, surrounds every galaxy, every star, every planet. Even now, as you rest and listen, that radiation passes quietly through the space around you. This ancient light is known as the cosmic microwave background. It is not dramatic. It does not flash or roar. It hums softly at 2.7 Kelvin, a whisper from a universe that had only just learned how to glow freely. If our eyes were sensitive to microwaves, the whole sky would shimmer gently, almost uniformly bright. Yet it is not perfectly smooth. Embedded within that glow are tiny variations in temperature, differences of only 1 part in 100,000. Imagine that scale for a moment. If the average temperature is 2.7 degrees above absolute zero, the fluctuations are only about 100,000th of that value. So small they almost disappear into stillness. Yet these slight differences mattered profoundly. Regions that were a little denser, a little warmer, held slightly more matter. Gravity, patient and persistent, began to amplify those differences over millions and then billions of years. From variations so subtle they could barely be measured, structure began to grow. Those tiny temperature ripples became the seeds of galaxies. Over time, gravity gathered gas into denser clumps. Clumps became clouds. Clouds became stars. Stars assembled into galaxies containing hundreds of billions of suns. Galaxies clustered together into larger formations. Superclusters stretched across unimaginable distances. All of it traced back to those faint irregularities. Just 1 part in 100,000, imprinted in the earliest light. And the origin of those irregularities reaches even further back. During a fleeting epoch called inflation, space itself expanded at an astonishing rate in less than a fraction of a second. Quantum fluctuations, microscopic variations smaller than an atom, were stretched to cosmic scales. What began as tiny ripples in the fabric of spacetime were magnified dramatically. Inflation froze those ripples into the structure of the universe. Think about that gently. A fluctuation smaller than an atom, born in a moment so brief it defies ordinary language, eventually becoming a galaxy that contains hundreds of billions of stars. A slight quantum whisper, magnified into spirals of light spanning 100,000 light-years. The scale shift is almost poetic. The smallest becoming the vastest. For hundreds of millions of years after recombination, the universe entered a long twilight known as the cosmic dark ages. There were no stars yet, only vast clouds of hydrogen drifting in expanding space. Gravity continued its quiet work, pulling matter inward wherever density was slightly higher. Slowly, patiently, the first luminous objects prepared to ignite. When the first stars finally formed a few 100 million years later, they were unlike most stars we see today. Many were massive, tens or even hundreds of times the mass of our sun. Because of their mass, they burned intensely and briefly. Some shone 1,000,000 times more brightly than our sun does now. Their light pierced the darkness, ending the cosmic dark ages and reionizing the surrounding hydrogen. The universe, once again, filled with radiance, this time from stars rather than plasma. Inside those first stars, nuclear fusion began transforming hydrogen into helium. In their cores, temperatures reached millions of degrees. Gravity squeezed matter so tightly that atomic nuclei fused together, releasing energy in the process. That energy is what makes a star shine. And in the most massive stars, fusion did not stop at helium. Continued, building heavier and heavier elements: carbon, oxygen, silicon, iron. When those early giants exhausted their fuel, they ended in spectacular supernova explosions. In those brief, violent moments, elements heavier than iron were forged: gold, uranium, and others, then scattered into space. The universe, once simple and composed mostly of hydrogen and helium, began to grow chemically complex. The atoms that would one day form planets, oceans, and living cells were created in those stellar furnaces. Carbon for organic molecules, oxygen for water, iron for blood, gold for the rare metals we treasure, all born in stars that lived and died billions of years ago. The universe, once uniform and nearly featureless, was now weaving complexity. Gravity continued to gather matter, forming an immense cosmic web. Filaments of galaxies stretched like glowing threads across the darkness, separated by vast voids where almost nothing resides. There is no central point to this web, no edge where it ends, only expansion, steady and ongoing. And through all of it, much of the shaping force remained invisible. Ordinary matter, the kind that forms stars and planets, makes up only a fraction of the total mass. Dark matter outweighs it by roughly 5-to-1. Though unseen, dark matter forms halos around galaxies, guiding their rotation and holding them together. Without it, stars at the edges would move too quickly and drift away into space. Even in its invisibility, dark matter quietly sculpts the cosmos. If you're still listening, gently type 1 in the comments. Let's continue drifting. The light released at that first moment of transparency did not vanish into emptiness. It stretched. As the universe expanded, space itself grew larger, and the wavelengths of those traveling photons lengthened with it. Light that began as a warm, visible glow gradually shifted into infrared, and then into microwaves. This is not because the photons aged or tired, but because the fabric of space expanded between each crest of the wave, pulling it wider and wider. If a wavelength once measured less than 1,000th of a millimeter, it now measures several millimeters across. That stretching cooled the radiation from thousands of degrees down to just 2.7 Kelvin, only 2.7 degrees above absolute zero. It is astonishingly cold, yet it fills the entire sky in every direction with almost perfect uniformity. If you could tune a simple radio to the right frequency and remove all modern signals, a small fraction of the static you would hear would be this ancient afterglow, whispering from nearly 13.8 billion years ago. But uniform does not mean featureless. Embedded within this background are those tiny temperature differences, 1 part in 100,000. To understand how small that is, imagine measuring a distance of 100 kilometers and finding a variation of only 1 meter. Or imagine a calm ocean where the surface differs in height by less than the thickness of a sheet of paper across a vast horizon. These slight variations marked regions where matter was slightly denser. In the language of gravity, slightly denser means slightly stronger pull. Over time, gravity amplifies what is uneven. Regions with more mass attract more matter. As more matter gathers, the gravitational pull increases further. It is a slow cascade, but relentless. Inflation had already prepared the pattern. In an unimaginably brief instant, far less than a second after the beginning, space expanded exponentially. During that period, quantum fluctuations, natural uncertainties at the smallest scales, were stretched outward. A fluctuation that might have been smaller than a proton was expanded to astronomical size. When inflation ended, those variations remained imprinted on the distribution of matter and energy. The cosmic microwave background is like a photograph of that early imprint, frozen at the moment the universe became transparent. We are, in a sense, looking at a baby picture of the cosmos. Over hundreds of millions of years, gravity gathered hydrogen into vast clouds. These clouds cooled and contracted. As they shrank, their centers became hotter and denser. Eventually, the pressure and temperature at the core became high enough for nuclear fusion to ignite. Hydrogen nuclei fused into helium, releasing energy according to the simple yet profound relation that energy equals mass multiplied by the speed of light squared. Even a tiny amount of mass converted into energy produces an enormous output because the speed of light squared is an immense number. That is why stars shine so powerfully. They are converting mass into light. The first generation of stars, often called population 3 stars, were likely massive and short-lived. Without heavier elements to cool their gas clouds efficiently, the collapsing regions tended to form large stars. Some may have been more than 100 times the mass of our Sun. Because luminosity increases steeply with mass, a star 10 times heavier than the Sun can shine thousands of times brighter. Some of these early giants may have been 1,000,000 times more luminous than our Sun, blazing intensely against the surrounding darkness. Their lives were brief, perhaps only a few million years, a heartbeat compared to the Sun's expected 10-billion-year lifespan. When such massive stars reached the end of their fusion cycles, they collapsed and exploded as supernovae. In those final moments, temperatures and pressures soared beyond anything sustained during their stable lifetimes. Elements heavier than iron were forged in fractions of a second. These explosions scattered enriched material into surrounding space, seeding future generations of stars with heavier elements. With each cycle of birth and death, the universe became more chemically diverse. Planets require elements like silicon and iron. Life requires carbon, oxygen, nitrogen, phosphorus. None of these were present in meaningful amounts at the beginning. They were created inside stars. As star formation continued, galaxies began to take recognizable shapes. Some formed graceful spirals with rotating disks and bright central bulges. Others formed massive elliptical structures, more spherical and diffuse. Yet beneath the visible stars, something unseen was guiding the architecture. Dark matter, making up roughly 27% of the universe's total energy content, formed gravitational wells long before most stars existed. Ordinary matter fell into these wells. In this way, dark matter halos acted like scaffolding for galaxies. The ratio is striking. Ordinary matter accounts for about 5% of the total cosmic energy budget. Dark matter outweighs it by roughly 5 to 1. That means most of the gravitational structure shaping galaxies is invisible. We infer its presence from the way stars move. At the edges of galaxies, stars orbit faster than they should if only visible matter were present. Without additional mass, those outer stars would not remain bound. They would drift away into intergalactic space. Dark matter provides the additional gravitational pull necessary to hold galaxies together. On the largest scales, galaxies are not scattered randomly. They form a vast cosmic web. Long filaments of galaxies stretch across hundreds of millions of light years, intersecting at dense nodes where clusters reside. Between these filaments lie enormous voids, regions tens of millions of light years across where very few galaxies exist. There is no center to this pattern and no boundary we can detect. Expansion carries everything outward, yet locally gravity binds matter together. The universe grows larger overall, even as galaxies assemble internally. From tiny fluctuations in a nearly uniform glow, an intricate structure emerged. From quantum ripples, a network of galaxies. From hydrogen and helium, the raw ingredients of life. The transformation was not sudden or loud. It unfolded slowly, guided by gravity and expansion, by cooling and fusion. The universe first learned to glow freely when atoms formed, but it learned to shine brilliantly when stars ignited. And through that gradual unfolding, complexity arose from simplicity, pattern from fluctuation, light from darkness. As the first generations of stars lived and died, the universe entered an era of increasing structure. What had once been a nearly uniform sea of hydrogen was now punctuated by islands of light. Each new star illuminated its surroundings, carving out bubbles in the neutral hydrogen that had filled space since recombination. Ultraviolet radiation streamed outward, ionizing atoms once more, separating electrons from protons again, but this time locally, around clusters of stars and young galaxies. Gradually, these bubbles grew and overlapped. Over hundreds of millions of years, the cosmos transitioned from darkness into a patchwork of glowing regions, until most of intergalactic space was once again ionized. This period is known as reionization, and it marked the true dawn of cosmic light. Inside these early galaxies, gravity orchestrated a delicate balance. Gas clouds fell inward under their own weight, heating as they compressed. When temperatures rose high enough, fusion ignited. Radiation from newborn stars pushed outward, resisting further collapse. The interplay between inward gravity and outward pressure created stability. A star exists in equilibrium, not collapsing and not exploding, but suspended in a long conversation between forces. For millions or billions of years, depending on its mass, this balance holds. The more massive the star, the greater the pressure required to support it. That means higher core temperatures and faster fusion rates. A star twice as massive as the Sun does not simply burn twice as fast. It burns far more quickly. Luminosity increases steeply with mass, so the most massive stars consume their nuclear fuel at extraordinary rates. Some early stars, perhaps 100 times the mass of the Sun, may have exhausted their hydrogen in only a few million years. In contrast, smaller stars, especially red dwarfs, can burn slowly and steadily for trillions of years. Mass determines destiny. Within stellar cores, fusion builds elements step by step. Hydrogen fuses into helium. In more massive stars, helium fuses into carbon and oxygen. As the core contracts and heats further, carbon can fuse into neon, magnesium, and sodium. Eventually, silicon fusion produces iron. Iron marks a turning point. Fusing iron does not release energy. It consumes it. When a core becomes dominated by iron, the star can no longer support itself through fusion. Gravity wins. The core collapses in a fraction of a second, and the outer layers rebound in a catastrophic supernova explosion. In that explosive instant, temperatures soar into the billions of degrees. Neutrons flood the environment. Heavy nuclei capture them rapidly, forming elements far beyond iron, gold, platinum, uranium. The explosion disperses these newly forged atoms into interstellar space. Over time, they mix with surrounding gas, becoming part of future stars and planetary systems. The calcium in bones, the oxygen in lungs, the iron in blood, all trace their origins to such events. The universe is not only expanding, it is recycling. As galaxies matured, they merged with one another. Gravity drew smaller systems together into larger ones. Collisions did not typically involve stars striking stars, because the distances between them are vast. Instead, gravitational interactions reshaped entire galaxies, triggering waves of star formation. Over billions of years, spirals grew larger, ellipticals formed from mergers, and clusters of galaxies assembled into enormous gravitationally bound systems containing hundreds or even thousands of member galaxies. Threading through all of this visible matter was the unseen framework of dark matter. Though it does not emit, absorb, or reflect light, its gravitational influence is unmistakable. Computer simulations that include dark matter reproduce the filamentary structure we observe across the sky. Without it, the growth of galaxies would have been too slow to match what we see. Dark matter began clumping even before ordinary atoms formed, because it does not interact with radiation in the same way. While photons kept ordinary matter smooth and uniform in the early universe, dark matter was free to begin forming dense regions earlier. When atoms finally formed and light decoupled, ordinary matter fell into the gravitational wells already prepared. On scales of hundreds of millions of light-years, the cosmic web becomes visible. Galaxies line up along filaments like dew along invisible threads. At intersections of these filaments lie massive clusters, where gravity binds enormous quantities of matter. Between them stretch voids, vast regions tens of millions of light-years across where very few galaxies exist. These voids are not completely empty, but they are extraordinarily sparse. If you could travel through one, you might journey for millions of light-years without encountering a single bright galaxy. There is no central point from which this web radiates. Expansion occurs everywhere at once. Every distant galaxy moves away from every other, carried by the stretching of space itself. The rate of expansion today can be described gently. For every megaparsec of distance, which is about 3.26 million light-years, galaxies recede at roughly 70 kilometers per second. Double the distance and the recession speed doubles. This is not motion through space in the ordinary sense. It is space itself expanding between objects. And yet, locally, gravity overcomes expansion. Within galaxies and clusters, matter remains bound. Stars orbit galactic centers. Galaxies orbit within clusters. On small scales, gravity weaves matter into complex forms, even as on large scales expansion continues to stretch the fabric outward. The universe holds both tendencies at once, gathering and dispersing, clustering and thinning. From faint temperature ripples in an almost uniform glow, this vast and intricate structure emerged. From fluctuations 1 part in 100,000, galaxies containing hundreds of billions of stars took shape. The transformation was gradual, unfolding over billions of years, guided by physical laws that operate with quiet consistency. The universe first learned to glow when atoms formed and light traveled freely. It then learned to shine when stars ignited, to enrich when they exploded, and to organize when gravity sculpted matter into a web that spans billions of light-years. The darkness between galaxies remains immense, but it is no longer empty of meaning. It is the stage upon which light continues to travel, carrying with it the story of a cosmos that began almost uniform and became astonishingly complex. As the web of galaxies continued to take shape, something subtle but essential was happening beneath the brilliance of stars. Most of the mass guiding this structure remained unseen. Dark matter does not glow, does not scatter light, does not absorb radiation. It interacts primarily through gravity. Yet its influence is written into the motion of galaxies and the bending of light itself. When astronomers measure how fast stars orbit at the edges of galaxies, they find speeds too high to be explained by visible matter alone. According to the balance between gravity and motion, a star orbiting far from a galactic center should slow down as distance increases, much like planets farther from the sun move more slowly. Instead, outer stars maintain nearly constant speeds. This flat rotation curve reveals that far more mass is present than we can see. Imagine a galaxy as a luminous disk embedded within a vast, invisible halo. The halo extends far beyond the visible edge, containing roughly 5 times as much mass as all the stars, gas, and dust combined. Without that halo, the gravitational pull would be too weak to hold the fast-moving outer stars in orbit. They would gradually drift away into intergalactic space. Dark matter acts as the quiet guardian of galactic structure, shaping rotation and stabilizing form. Its presence is also revealed when light from distant galaxies passes near massive clusters. Gravity bends the path of light, a phenomenon predicted by general relativity. When enough mass is concentrated in one region, it can distort background light into arcs or even multiple images. By measuring how strongly light is bent, astronomers can map the distribution of mass in clusters. These maps show far more mass than luminous matter alone accounts for. The additional mass aligns with what we call dark matter. Even though it cannot be seen directly, its gravitational signature is unmistakable. On the largest scales, dark matter was crucial in amplifying the tiny fluctuations imprinted in the cosmic microwave background. Remember those variations, only 1 part in 100,000. After recombination, ordinary matter began to fall into regions that were already slightly denser. But dark matter had started clustering even earlier because it did not interact with radiation in the same way charged particles did. While photons kept ordinary matter relatively smooth before recombination, dark matter quietly gathered into clumps. When atoms formed and light streamed freely, ordinary matter finally felt the full pull of those dark scaffolds. In this way, the invisible shaped the visible. As galaxies formed along filaments of dark matter, clusters emerged at intersections where gravitational attraction was strongest. Some clusters contain thousands of galaxies bound together, along with enormous reservoirs of hot gas glowing in X-rays. Yet even there, visible matter accounts for only a portion of the total mass. The majority remains dark. Across billions of light-years, the cosmic web reflects this hidden architecture. And still, expansion continues. The universe does not expand into something outside itself. Rather, distances between unbound objects increase over time. The scale factor, a measure of cosmic size, grows steadily. If we imagine marking 2 galaxies separated by 100 million light-years, over time that distance increases. The rate of this increase today is described by a constant that relates velocity to distance. For each megaparsec of separation, roughly 70 kilometers per second of recession speed is added. So at 10 megaparsecs, the recession speed is about 700 kilometers per second. At 100 megaparsecs, about 7,000 kilometers per second. The farther away a galaxy is, the faster it appears to move away from us, not because we occupy a special location, but because expansion is uniform everywhere. There is no center from which galaxies flee. Every observer anywhere in the universe would see distant galaxies receding in the same way. This uniform expansion means there is no preferred direction, no boundary we can approach. The observable universe is limited only by the time light has had to travel since the beginning. Beyond that horizon, more space almost certainly exists, expanding as well, though its light has not yet reached us. Within galaxies, gravity counters expansion. The Milky Way does not expand internally. Its stars remain bound, orbiting the galactic center in a dance lasting hundreds of millions of years per rotation. Even clusters of galaxies remain gravitationally bound. Expansion dominates only on sufficiently large scales, where gravity cannot overcome the stretching of space. The universe is therefore layered, bound systems nested within expanding space, islands of structure within a widening ocean. From a nearly uniform glow at 2.7 Kelvin to the immense web of galaxies we observe today, the transformation has been gradual yet profound. A temperature variation smaller than 1/10,000% became the blueprint for everything. Quantum ripples, once microscopic, now span billions of light years. Hydrogen clouds collapsed into stars. Stars forged elements. Supernovae enriched space. Galaxies assembled within halos of invisible matter. Clusters formed at the intersections of filaments. Voids opened between them, vast and almost empty. And through it all, the universe remained governed by a small set of consistent principles. Gravity pulling inward, expansion stretching outward, fusion releasing energy from mass. No sudden interruption, no central command, only laws unfolding patiently over time. The cosmos learned to glow when atoms formed and light traveled freely. It learned to shine when stars ignited. It learned to build complexity through cycles of birth and death. Even now, as you listen, that ancient background radiation still permeates space, cooled to 2.7 Kelvin. The same photons released when the universe first became transparent continue their journey. They pass through galaxies, across clusters, through the quiet darkness of intergalactic voids. They have traveled for nearly 13.8 billion years without stopping. In a sense, the universe is still glowing from that first moment of clarity. And every structure we see, the spirals, the clusters, the web itself, traces its origin back to that subtle transition when light was finally set free. If we step back now and hold the entire sequence gently in our minds, the transformation becomes almost meditative. At first, there was a hot, dense state where light and matter were inseparable, locked together in a radiant fog. Then, at 380,000 years, the universe cooled enough for protons and electrons to unite into neutral hydrogen. In that union, transparency was born. Photons, once scattered endlessly, were released to travel freely. That release was not explosive or loud. It was a quiet letting go. And those photons are still traveling, stretched by expansion into the soft microwave glow that surrounds everything at 2.7 Kelvin. Inside that faint background are the smallest differences imaginable, just 1 part in 100,000. If the temperature were perfectly smooth, structure might never have formed. But it was not perfectly smooth. Some regions were slightly denser, slightly warmer. Gravity noticed. Gravity always notices. Over time, those tiny variations grew. Matter flowed toward slightly denser regions, deepening the imbalance. The denser a region became, the stronger its gravitational pull, and the stronger its pull, the more matter it gathered. This feedback unfolded slowly, over millions and billions of years, shaping the architecture of the cosmos. Quantum fluctuations during inflation provided the original pattern. A fluctuation smaller than an atom was stretched across astronomical distances in less than a second. That stretching imprinted a map of subtle density differences across space. When the universe became transparent, that map was frozen into the cosmic microwave background. What we observe today as tiny temperature variations are the fingerprints of those earliest moments. From something subatomic emerged something intergalactic. A few 100 million years after transparency, gravity had drawn hydrogen into dense clouds large enough to ignite fusion. The first stars blazed into existence, some perhaps 1,000,000 times more luminous than our sun. Their light pierced the cosmic dark ages. They transformed simple hydrogen into helium and then into heavier elements. When they died, they exploded, scattering carbon, oxygen, iron, and even gold into surrounding space. these elements did not vanish. They mixed with interstellar gas, becoming the ingredients of new stars, new planets, and eventually life. The oxygen in a breath, the calcium in bone, the iron in blood, all forged in ancient stellar cores. The universe, once nearly uniform, became richly structured. Galaxies formed along filaments of a vast cosmic web. Clusters gathered at the intersections of those filaments. Between them stretched immense voids, regions so empty that a traveler could cross millions of light-years without encountering a bright galaxy. There is no central hub to this web, no edge where it fades into nothing. Expansion carries galaxies away from one another uniformly. Every distant region recedes from every other, with speeds proportional to distance. For each megaparsec of separation, about 70 kilometers per second of recession is added. It is not galaxies racing through space, but space itself stretching. And beneath it all lies the quiet dominance of dark matter. Ordinary matter, the kind that forms stars and planets, accounts for only about 5% of the cosmic total. Dark matter outweighs it roughly 5 to 1. Though invisible, it forms massive halos around galaxies, providing the gravitational glue that keeps them intact. Without it, outer stars would move too quickly and drift away. On even larger scales, dark matter shapes the filaments and clusters of the cosmic web. The visible universe is built upon an unseen foundation. So when we say the universe first learned to glow, we are speaking of more than just light traveling freely. We are speaking of the beginning of visible structure. Transparency allowed radiation to carry information across space. Tiny variations became seeds. Seeds became galaxies. Galaxies became crucibles for stars. Stars became forges for elements. Elements became the chemistry of planets and, eventually, consciousness. There is something profoundly calming in this continuity. No abrupt leaps, no chaotic randomness without pattern. The same physical laws that governed the first atoms govern stars today. The same gravity that amplified 1 part in 100,000 fluctuations now holds galaxies together. The same expansion that stretched early photons continues to stretch space tonight. As you rest, the cosmic microwave background still fills the sky, cooled but persistent. Dark matter still shapes the motion of galaxies. Stars still fuse hydrogen into helium, converting mass into light with steady precision. The universe is not rushing. It unfolds at scales so vast that even billions of years are chapters in a longer story. From a glowing fog to a transparent cosmos, from subtle ripples to immense clusters, the journey has been gradual and patient. Imagine again that first moment of clarity, when light was finally free to travel without constant scattering. That freedom allowed the universe to reveal itself. Every telescope image, every galaxy catalog, every map of the cosmic web traces back to that quiet transition. The cosmos did not shout when it became transparent. It simply softened, cooled. It let light pass. And from that gentle shift, everything we see and everything we are eventually followed. If you're still listening, gently type 1 in the comments. Let's continue drifting. Look up at the night sky and you see stars. Points of light scattered across darkness, steady and familiar. But those stars, as numerous as they seem, make up only a small fraction of what truly exists. Everything you have ever touched, your skin, the air, the oceans, the distant nebulae glowing in telescopes, belongs to a thin layer of reality. Roughly 5% of the universe is ordinary matter, the kind built from atoms. About 27% is dark matter, invisible and silent, revealing itself only through gravity. And nearly 68% is something stranger still. Dark energy, a subtle pressure woven into space itself, gently pushing the cosmos outward at an ever-increasing pace. For most of the 20th century, astronomers assumed that expansion, which began with the Big Bang, must be slowing down. Gravity, after all, pulls. Galaxies attract one another. Matter gathers. It seemed natural that the universe would gradually decelerate, like a ball thrown upward, slowing as it climbs. But in 1998, observations of distant exploding stars, type Ia supernovae used as cosmic distance markers, revealed something unexpected. The expansion was not easing. It was accelerating. The farther away the galaxy, the faster it appeared to be receding. Not because it was racing through space, but because space itself was stretching more quickly with time. Imagine placing dots on the surface of a balloon. As you inflate it, every dot moves away from every other dot. Now imagine that the inflation itself speeds up. That is what our universe is doing. Not exploding into emptiness, but expanding everywhere at once. There is no central point from which everything flies. Every galaxy sees others moving away. Every region is carried along by this quiet, persistent growth. Billions of years from now, this acceleration will reshape the sky. Distant galaxies, those we can barely see today, will drift so far that their light will never reach us again. They will cross what is called the cosmological horizon. Not a wall, not an edge, but a limit set by the speed of light and the expansion of space. Beyond that horizon, events still happen. Stars still burn, but their signals will never arrive. The observable universe will shrink, not in size, but in visibility. And yet, within galaxies, life continues slowly and patiently. Stars do not rush. Our sun, about 4.6 billion years old, is roughly halfway through its expected 10 billion year lifetime. In its core, hydrogen nuclei fuse into helium at a steady, measured pace. Each second, about 4 million tons of matter convert into energy according to Einstein's equation. Energy equals mass times the speed of light squared. Even spoken gently, that transformation sounds immense. 4 million tons per second. And still, the sun burns calmly, without drama, sustaining warmth on a small planet orbiting at just the right distance. Massive stars live differently. A star 10 times heavier than the sun burns through its fuel far more quickly. Pressure and temperature in its core rise higher. Fusion accelerates. What might last 10 billion years for our sun may last only tens of millions of years for a giant star. They live brightly and briefly, like cosmic sparks. When their fuel runs out, gravity takes over. The core collapses in seconds. Outer layers explode outward in a supernova, scattering elements into space: carbon, oxygen, iron, the building blocks of worlds and living things. What remains after such a collapse can be astonishing. If the core is not too heavy, it becomes a neutron star, a sphere only about 20 kilometers across, yet containing more mass than our sun matter. There is compressed so tightly that electrons and protons merge into neutrons. A teaspoon of this material would weigh billions of tons. It is difficult to imagine. So instead, let it remain as a quiet fact. An entire star folded into something the size of a city. Some neutron stars become magnetars. Their magnetic fields are trillions of times stronger than Earth's. If one were placed halfway to the moon, its field could erase data from credit cards on Earth. Fortunately, they are far away. They spin, they pulse, they occasionally release bursts of high-energy radiation, and then, over time, they calm. If the collapsing core is heavier still, gravity overwhelms every known force. A black hole forms, not an object in the usual sense, but a region where escape becomes impossible. An event horizon marks the boundary. Cross it, and even light cannot return. From the outside, black holes appear quiet. But when two of them orbit one another, something extraordinary happens. They lose energy by emitting ripples in space-time itself, gravitational waves. As they spiral inward and merge, those ripples spread outward at the speed of light. In 2015, detectors on Earth measured such a ripple for the first time. A faint stretching and squeezing of space, smaller than the width of a proton, arriving from a collision more than 1 billion light-years away. A prediction made a century earlier had finally been confirmed. Space itself can tremble. Reality can ring like a bell. The universe is quieter than we assume, slower, vast beyond urgency. If you are still here, softly type 2 in the comments. Let the silence deepen. Dark matter does not shine. It does not reflect light, absorb it, or emit it. If you were surrounded by it, you would not see a shadow or feel a touch. And yet, without it, galaxies as we know them could not exist. When astronomers measure how fast stars orbit within spiral galaxies, they find something puzzling. Stars near the outer edges move far faster than visible matter alone can account for. According to simple gravity, the farther a star is from the center, the slower it should travel. Instead, the rotation curves remain flat. The outer stars move almost as quickly as those nearer the core, as if held in place by an unseen mass. That unseen mass is dark matter, forming vast halos around galaxies, extending far beyond the luminous disks we photograph. In fact, for every kilogram of ordinary matter, there are roughly 5 kilograms of dark matter shaping the same region. It outweighs the familiar world, yet it remains invisible. As you lie still, dark matter particles are passing through your body, trillions of them each second. They do not collide with your atoms in any noticeable way. They do not disturb your sleep. They move as though everything solid were mostly empty space, which, in truth, it is. Atoms themselves are mostly void, tiny nuclei surrounded by clouds of probability. So dark matter drifts silently through you, through Earth, through stars. It binds galaxies together, yet it leaves you untouched. That quiet presence makes up more than a quarter of the universe. And then there is dark energy. If dark matter acts like glue, dark energy acts like a gentle pressure pushing space apart. We do not know its nature. We measure its effect. The expansion of the universe is described by a value called the Hubble constant, about 70 kilometers per second per megaparsec. Spoken slowly, that means that for every megaparsec of distance, about 3 million light-years, galaxies appear to recede 70 kilometers per second faster. Double the distance, double the speed. The farther away something is, the faster space stretches between us and it. This stretching is not wind, not motion through space, but the growth of space itself. If dark energy remains constant, the future will unfold in a predictable calm. Galaxies outside our local group will slip beyond view. The night sky, billions of years from now, will grow emptier. Future astronomers, if any exist, may look up and see only the merged remnant of the Milky Way and Andromeda, unaware that the wider cosmos once blazed with trillions of galaxies. They will inhabit an island universe, surrounded by darkness not because nothing is there, but because expansion has carried distant light beyond reach. Meanwhile, within galaxies, stars continue their slow fire. The sun fuses about 600 million tons of hydrogen into helium every second. Only a small fraction of that mass becomes energy, about 4 million tons converted according to energy equals mass times the speed of light squared. The rest remains as helium ash in the core. Over time, hydrogen will thin. In roughly 5 billion years, the core will contract in heat, and the outer layers will swell outward. The sun will become a red giant, perhaps large enough to engulf Mercury and Venus. Earth's oceans will long have evaporated. But this transformation will be gradual on human scales. Millions of years will pass between subtle changes. Massive stars do not enjoy such patience. A star 20 times the mass of the sun may live only 10 million years. It fuses heavier and heavier elements in layered shells, hydrogen to helium, helium to carbon, carbon to oxygen, and onward toward iron. Iron marks a limit. Fusing iron does not release energy. It consumes it. When the core becomes iron-rich, fusion halts. Gravity wins. In less than a second, the core collapses. The outer layers rebound in a supernova explosion so bright it can briefly outshine an entire galaxy. For a short time, that single star radiates more energy than billions of suns combined. Then it fades, leaving behind a neutron star or black hole and an expanding cloud of enriched gas. Those clouds drift for thousands of years, mixing with interstellar space. From them, new stars and planets form. The calcium in your bones, the oxygen you breathe, the iron in your blood were forged in such furnaces. The slow fire of stars becomes the chemistry of life. Even black holes, often imagined as eternal, are not permanent. According to quantum theory, they emit a faint radiation at their edges. Over unimaginable spans of time, this Hawking radiation causes them to lose mass. A black hole with the mass of our sun would take on the order of 10 to the 67th power years to evaporate. To say that number gently, one followed by 67 zeros, longer than the current age of the universe by a factor so vast it almost dissolves meaning. And yet it is finite. Perhaps, too, there exist primordial black holes formed fractions of a second after the Big Bang, when density fluctuations were extreme. They would not be born from stars, but from the early universe itself, tiny knots of gravity that survived until now. We have not confirmed their existence, but the possibility remains. Ancient, silent, wandering through space since time's first heartbeat. The invisible majority shapes everything. The slow fire of stars writes chemistry into darkness, and all of it unfolds without hurry, without demand. The universe does not strain. It expands, it burns, it cools, vast beyond urgency. Let the quiet stretch a little longer. When black holes merge, the universe briefly becomes louder than we ever imagined, though not in sound, but in motion. Two invisible objects, each perhaps dozens of times more massive than the sun, spiral around one another for millions or billions of years. Their orbit tightens slowly, almost imperceptibly, as they radiate energy away in the form of gravitational waves. These waves are not vibrations in air. They are distortions in spacetime itself, stretching distance in one direction while compressing it in another. As the black holes draw closer, the waves grow stronger and faster, until in the final fraction of a second they collide and become one. In that instant, more energy can be released in gravitational waves than all the stars in the observable universe emit as light at that moment. And yet, by the time those waves reach Earth, they are so faint that they alter the length of a 4-kilometer detector arm by less than 1,000th the width of a proton. The most violent events in existence arrive as whispers. This contrast defines the cosmos. Immense forces unfolding with patient quiet. Even neutron stars, remnants of collapsed suns, live out their strange existence without spectacle most of the time. Some spin hundreds of times per second, beams of radiation sweeping across space like lighthouse beams. To distant observers, they pulse with astonishing regularity, ticking more precisely than many atomic clocks. Others, magnetars, carry magnetic fields so intense they warp atomic structure. If one passed close enough, it could rearrange the electrons in matter itself. Yet they remain distant, small, no wider than a city, suspended in darkness, cooling over millions of years. Gravity, which sculpts galaxies and collapses stars, is both relentless and gentle. It builds structure from near uniformity. After the early universe cooled and the first atoms formed, tiny fluctuations in density, just 1 part in 100,000, became seeds. Where matter was slightly denser, gravity gathered more matter. Over hundreds of millions of years, those denser regions formed the first galaxies. Dark matter halos provided the scaffolding. Gas fell inward, heated, and ignited the first stars. From those stars came light, and from their deaths came complexity. Yet most of this drama unfolds on timescales far beyond instinct. A galaxy like the Milky Way takes about 225 million years to complete one orbit around its center. Since dinosaurs walked the Earth, Our solar system has circled the galaxy only once. Since the first simple life forms appeared in Earth's oceans, it has circled fewer than 20 times. The motions that define the cosmos are vast and slow, loops within loops, spirals within spirals. Even now, the Sun travels around the galactic center at roughly 220 kilometers per second, carrying Earth with it in a gentle helical path. You do not feel this motion. You sit still while traveling through space at enormous speed. Black holes, too, participate in these grand movements. At the center of most galaxies lies a supermassive black hole, millions or billions of times the mass of the Sun. Our own galaxy hosts one about 4 million solar masses. It does not devour everything nearby. It sits mostly quiet, stars orbiting it in elongated paths, completing full circuits in years or decades. Occasionally, gas drifts too close and flares brightly before disappearing. But most of the time, it simply anchors the core, shaping stellar motion without spectacle. Even these giants will not endure forever. Through Hawking radiation, black holes slowly lose mass. The process is almost inconceivably gradual. A stellar mass black hole would require around 10 to the 67th power years to fully evaporate. A supermassive black hole would take far longer still. To compare, the universe today is about 13.8 billion years old, which is roughly 10 to the 10th power years. 10 to the 67th power dwarfs that span beyond comprehension. If written out, it would be a 1 followed by 67 zeros. Yet the number is finite. Even the darkest objects fade. And perhaps there are black holes older than any star. In the first fraction of a second after the Big Bang, density fluctuations may have been extreme enough to collapse directly into tiny black holes. These primordial black holes would not form from stellar death, but from the raw energy of the early cosmos. Some might be small, perhaps the mass of a mountain compressed into a microscopic region. Others might be heavier. If they exist, they could drift through the universe unnoticed, silent fossils from time's beginning. We have not yet confirmed them, but physics allows the possibility. The universe, then, is layered in invisibility. Dark matter outweighs ordinary matter. Dark energy dominates them both. Black holes hide behind horizons. Gravitational waves pass through everything without resistance. Neutrinos stream from the sun and distant supernovae, barely interacting with atoms as they cross entire planets. Most of reality is subtle. Most of its structure is inferred rather than seen. And still, within this vastness, stars continue their slow fire. In the sun's core, temperatures reach about 15 million degrees Celsius. Hydrogen nuclei overcome their mutual repulsion and fuse, releasing energy that takes thousands of years to migrate outward through dense plasma before emerging as sunlight. The photons warming your skin tonight began their journey in the solar core long before human civilization existed. Energy moves patiently, even in fusion. Everything unfolds without urgency. Galaxies drift apart faster each billion years. Stars ignite and fade across epochs. Black holes merge and whisper their presence through space-time. The cosmos is not rushing toward an ending. It is simply following its equations, expanding, cooling, transforming. vast beyond urgency, quiet beyond assumption. Remain with that stillness a little longer. If we could step outside of time and watch the universe in accelerated motion, we would see an ocean of structure slowly shifting. Galaxies would drift like glowing embers carried on a widening tide. Dark matter halos would move invisibly, guiding the dance. Space itself would stretch, not violently, but persistently, as though the cosmos were breathing outward with no need to inhale again. That outward breath is powered by dark energy, the dominant ingredient of reality, making up nearly 70% of everything that exists. It does not clump. It does not gather. Instead, it acts uniformly embedded in space itself. And as space expands, there is more of it. More space means more dark energy, and more dark energy means faster expansion. A subtle feedback loop written into the geometry of existence. Over billions of years, this acceleration will change the visible universe. Right now, we can observe galaxies up to tens of billions of light years away, their light stretched into faint red and infrared glows. But because expansion accelerates, there are galaxies whose light emitted today will never reach us. They are already receding faster than light, not because they move through space so quickly, but because the space between us grows too fast to bridge. Nothing locally breaks the cosmic speed limit. It is space itself that stretches. In the far future, even galaxies we can see now will cross that threshold. The observable universe will gradually contract to a local island of gravitationally bound systems. Our own galaxy and the Andromeda Galaxy are destined to merge in roughly 4 billion years. Their mutual gravity will overcome expansion at that scale. Stars will rarely collide, as distances between them are vast, but their orbits will be reshaped. Gas clouds will compress, igniting bursts of star formation. Over time, the two spirals will blend into a single, larger elliptical galaxy. This new system will drift alone in an increasingly dark cosmos, as more distant galaxies vanish beyond the horizon. Within this merged galaxy, stellar evolution will continue its patient rhythm. Red dwarfs, the smallest and most common stars, will outlive all others. Some of them can burn for trillions of years, slowly converting hydrogen into helium with extraordinary efficiency. While massive blue stars blaze and die in mere millions of years, red dwarfs endure quietly, dim but persistent. Long after the sun has expanded into a red giant and shed its outer layers to become a white dwarf, these faint red embers will still shine. The era of bright star formation will fade, replaced by a long twilight dominated by small, steady lights. Eventually, even red dwarfs will exhaust their fuel. They will cool into white dwarfs, dense Earth-sized remnants composed mostly of carbon and oxygen. White dwarfs shine not by fusion, but by residual heat. They radiate slowly, cooling over billions upon billions of years. Given enough time, far more than the current age of the universe, they will grow cold and dark, becoming what physicists call black dwarfs. No black dwarfs exist yet, because the universe is not old enough. But in the distant future, they may fill the galaxy. Silent, invisible relics of once luminous stars. Neutron stars will also persist for unimaginable spans. Their intense gravity and dense matter make them stable, cooling gradually as they radiate away energy. Some will spin down, their pulses slowing until they become nearly undetectable. Black holes, though seemingly eternal, will dominate the late stages of cosmic history. As other structures fade, black holes will remain, occasionally merging when chance encounters bring them together. Each merger will release gravitational waves, briefly stirring space-time before quiet returns. But even black holes are temporary. Through Hawking radiation, they lose mass at an almost imperceptible rate. The smaller the black hole, the faster it evaporates. Tiny primordial black holes, if they exist, might have already vanished in bursts of high-energy radiation. Larger ones will take far longer. A black hole with the mass of the Sun would require around 10 to the 67th power years to fully evaporate. A supermassive black hole could last 10 to the 100th power years or more. These numbers are so vast that language struggles to contain them, yet they are finite. The equations of quantum mechanics and gravity imply that even the darkest objects slowly leak energy into the vacuum. As black holes evaporate, the universe approaches what is called heat death. Not an explosion, not a collapse, a gradual smoothing out. Energy differences which allow work to be done will diminish. Temperature variations will fade. Matter may even decay at the smallest scales, if certain theories prove correct. Protons themselves could have lifetimes longer than 10 to the 34th power years, but not infinite. If they decay, atoms dissolve. Planets disintegrate. Structures lose coherence. The cosmos becomes a thin distribution of particles and radiation, drifting in an ever-expanding void. This vision is not violent. It is quiet. Entropy, the measure of disorder, increases until it reaches a maximum. No gradients remain to power stars, to drive chemistry, to create complexity. Time continues, but nothing changes. A universe stretched so thin that events become rare beyond imagination. And yet, even this may not be the final word. Some theories suggest dark energy could evolve, perhaps weakening, perhaps strengthening. If it were to intensify dramatically, expansion might accelerate to such an extent that galaxies, stars, and even atoms are torn apart in a distant Big Rip. Alternatively, if dark energy changes sign or fades, gravity could one day reclaim dominance, halting expansion and reversing it in a slow contraction. The cosmos might collapse into a hot, dense state once more, a big crunch. Some speculative models imagine that such a crunch could rebound into another expansion, a cosmic bounce, where endings become beginnings. We do not yet know which path reality will take. Observations currently favor continued acceleration, a long glide towards stillness. But uncertainty remains. The universe has surprised us before. It revealed dark energy when we expected deceleration. It revealed dark matter when stars moved too quickly. It revealed gravitational waves a century after they were predicted. Its story unfolds gradually, layer by layer. For now, what is certain is this: we inhabit a brief luminous era. Stars shine. Galaxies are visible across billions of light years. structure is rich and varied. The invisible majority, dark matter and dark energy, shapes everything quietly. And in the midst of this vast unfolding, consciousness has emerged on at least one small world orbiting a modest star. The universe is quieter than we assume, slower than instinct suggests, vast beyond urgency. Let that vastness settle around you like a gentle horizon, stretching without demand, expanding without haste. When we step back far enough, the story of the universe becomes less about brilliance and more about patience. The night sky feels immediate, but almost everything you see is ancient light. Some stars are a few dozen light years away, their glow beginning its journey before modern history. Others are thousands of light years distant, and the faintest galaxies visible in powerful telescopes shine from billions of years in the past. Light itself moves at nearly 300,000 kilometers per second, the fastest speed allowed. Yet even that speed is slow compared to cosmic scale. The observable universe stretches about 46 billion light-years in every direction, not because it is older than its age, but because space has expanded while light traveled. Expansion is not a force that pushes like wind. It is geometry changing over time. The equations of general relativity describe spacetime as dynamic, curved by mass and energy. Add dark energy to that framework, and the curvature evolves differently. On the largest scales, gravity cannot overcome expansion anymore. Galaxies outside gravitationally bound groups drift away, and the rate of separation grows. If you imagine marking the distance between two faraway galaxies today and checking again in a billion years, the gap will be larger than simple linear motion would predict. Acceleration accumulates, and yet, on smaller scales, gravity still reigns. Our solar system remains intact because the gravitational pull between the Sun and its planets is far stronger than the subtle stretching of space at that distance. The Milky Way holds together for the same reason. Even the local group of galaxies, including Andromeda and dozens of smaller companions, is gravitationally bound. Expansion shapes the vast tapestry, but gravity weaves the local threads. Stars continue their slow transformation within this expanding backdrop. In the Sun's core, fusion proceeds through a chain of reactions that converts hydrogen into helium. Four hydrogen nuclei combine through intermediate steps into one helium nucleus. A small fraction of mass disappears in the process, transformed into energy. That energy diffuses outward, taking thousands to hundreds of thousands of years to reach the surface, then only 8 minutes to cross the distance to Earth. The warmth you feel from sunlight today may have begun its outward journey long before recorded human history. Energy moves through stars like a slow pulse. More massive stars follow more complex fusion pathways. They build layered cores, each shell fusing a different element. The final collapse of a massive star is not gradual. It is sudden. When iron accumulates at the center, fusion can no longer support the core. In less than a second, gravity compresses matter so intensely that protons and electrons merge into neutrons. The core rebounds and a shockwave tears through the outer layers. The explosion synthesizes heavy elements through rapid neutron capture, creating gold, platinum, and uranium. These atoms scatter into space, later becoming part of planets and perhaps of living beings. Destruction becomes distribution. Black holes form when gravity compresses matter beyond neutron degeneracy pressure. Their defining feature, the event horizon, marks a boundary from which no signal can escape. To an outside observer, matter falling toward a black hole appears to slow, its light reddening and fading as it approaches the horizon. Time dilation becomes extreme. From the perspective of the infalling matter, however, the crossing happens in finite time. Space and time exchange roles near the singularity in ways that strain intuition. These objects do not simply consume, they alter the geometry around them. Gravitational waves add another dimension to this quiet drama. When massive bodies accelerate asymmetrically, they generate ripples in spacetime that propagate outward at light speed. The detection of such waves confirmed that spacetime is not a static stage but an active participant. The merger of two black holes converts a portion of their mass directly into wave energy, briefly outshining all stars combined, though invisibly. The wave passes through planets and people alike without resistance, stretching and compressing space by fractions too small to feel. Reality itself oscillates. Even in emptiness, physics continues. The vacuum is not truly empty. Quantum fields permeate space, fluctuating constantly. Particle-antiparticle pairs flicker into and out of existence in times too brief to measure directly. This restless background contributes to vacuum energy, which may be related to dark energy. The precise connection remains uncertain, one of the great unsolved problems in theoretical physics. The numbers predicted by simple quantum field calculations differ dramatically from what cosmology measures. Somewhere between these frameworks lies a deeper understanding still waiting to be uncovered. The long-term future, if expansion continues to accelerate, leads toward isolation and cooling. After trillions of years, star formation will cease as gas supplies are exhausted or locked within remnants. White dwarfs, neutron stars, and black holes will dominate. Gravitational interactions may eject some objects from galaxies entirely, sending stars and remnants drifting through intergalactic space. Eventually, only black holes will remain as significant gravitational centers. Over spans far exceeding 10 to the 60th power years, they too will evaporate through Hawking radiation, ending not in explosion but in gradual dissolution. What remains after that is difficult to picture. A thin distribution of low-energy particles and radiation spread across a vast and ever-growing space. No structure large enough to form stars. No temperature differences to power change. Entropy at its maximum. A universe that has spent its gradients. And yet, here and now, we inhabit a luminous middle chapter. 5% ordinary matter. 27% dark matter, 68% dark energy. These proportions define the stage on which stars burn and galaxies drift. The invisible majority shapes the visible minority. The slow fire of fusion writes elements into space. Gravity sculpts structure from fluctuation. Expansion carries everything gently outward. The universe is quieter than we assume, slower than our instincts expect. vast beyond urgency. In that vastness, your existence is neither central nor insignificant. It is a brief expression of cosmic history becoming aware of itself. As expansion continues and stars persist in their measured burning, there is no rush. The equations unfold at their own pace. The cosmos does not hurry toward its ending. It simply evolves, steadily, silently, and immensely. If you are still here, softly type 2 in the comments. Let the silence deepen. Now we drift forward, not millions, but trillions of years. The night sky will not disappear all at once. It will thin slowly, like breath fading on cold glass. Star formation, which today still quietly continues in hidden clouds of hydrogen, will gradually slow. Galaxies will use up their reserves of cold gas, the raw material from which new suns are born. Each generation of stars locks hydrogen into heavier elements, and with every supernova, more gas is heated or blown away, less able to collapse again. Over the next 100 billion years, the bright spiral arms of galaxies will grow quieter. The blue-white giants, short-lived and brilliant, will already be gone. Their fierce light, which once shaped nebulae and sparked new star birth, will exist only in memory. What remains will be smaller stars, steady, patient, red. Red dwarfs will become the quiet rulers of the cosmos. These small stars burn their fuel with extraordinary efficiency. While a star like our Sun shines for about 10 billion years, a red dwarf can glow for trillions, not with blazing intensity, but with endurance. Their light is dimmer, softer, deeper red. Around them, planets may continue circling long after larger stars have faded. If any civilizations exist in that far future, they will grow beneath crimson skies, orbiting embers that outlast almost everything else. As trillions of years pass, even these red dwarfs will begin to exhaust their hydrogen. One by one, they too will dim. No sudden flash, no grand explosion, just a gradual cooling. By then, galaxies will look very different. Collisions will have reshaped them. The Milky Way and Andromeda will have merged long before, forming a single vast elliptical galaxy. Over time, gravitational interactions will scatter stars into wider and wider orbits. Some will be ejected entirely, flung into intergalactic darkness by close encounters. The universe will not tear itself apart violently. It will loosen. Eventually, what remains inside galaxies will mostly be stellar remnants. White dwarfs, dense cores left behind by stars like our Sun, will continue radiating away their stored heat. At first they glow white, then red, then infrared. Over quadrillions of years, they cool further, becoming faint black dwarfs. Not yet real in our current universe because not enough time has passed. But in that distant era, they will be everywhere. Silent, cold, invisible. Neutron stars will still exist, small and impossibly dense. Some may still spin, though more slowly than before. Pulsars that once flashed with perfect rhythm will lose energy, their rotations stretching longer and longer until even their steady ticking fades into stillness. And black holes, those deep wells in space-time, will dominate the gravitational landscape. Supermassive black holes at the centers of merged galaxies will remain, along with countless smaller ones formed from ancient stars. In a universe emptied of new light, black holes will be among the last engines of structure. All of this unfolds under a simple, measured expansion. Even now, space itself stretches at roughly 70 kilometers per second for every megaparsec of distance. That means that for every 3 million light-years between galaxies, the space in between grows by about 70 kilometers each second. It does not feel dramatic. It does not shake the ground, but it is relentless. In trillions of years, that steady expansion will have carried galaxies so far apart that most will lie forever beyond each other's horizons. And still, there will be no rush. The far future is not an explosion. It is a soft dimming, patient unwinding of light. As the ages lengthen beyond trillions into numbers so vast they almost dissolve meaning, the universe enters what physicists sometimes call the degenerate era. It is a quiet name for a quiet time. Ordinary stars are no longer being born. The last red dwarfs have exhausted their fuel. What remains are remnants. White dwarfs cooling into black dwarfs, neutron stars drifting like heavy cinders, and black holes anchoring the scattered remains of galaxies. Space between these objects continues to stretch. The background glow of the cosmos, once 2.7 Kelvin in our era, keeps cooling, its wavelength lengthening as expansion thins everything out. Temperature differences shrink. Contrast fades. In this long twilight, encounters still happen, but rarely. A wandering black dwarf may pass near a neutron star. Two stellar remnants might spiral together after losing energy through gravitational radiation. Occasionally, a collision will flare briefly, a last flash in a universe that has largely gone dark. But such events become increasingly uncommon as distances grow. Gravity still works, yet there is less and less nearby for it to gather. Black holes, however, continue to shape what remains. Over unimaginable timescales, even they are not eternal. Through Hawking radiation, they very slowly lose mass. The process is almost imperceptible. For a black hole with the mass of our Sun, the evaporation time is on the order of 10 to the 67th power years. A supermassive black hole may last far longer still. But given enough time, even these giants begin to shrink. Their event horizons contract. Their temperature, inversely related to their mass, rises as they become smaller. In the final moments, after duration so long that all earlier cosmic history feels like a heartbeat, they release a faint burst of energy and disappear. No drama on a galactic scale, just one more quiet subtraction from an already sparse cosmos. If dark energy continues behaving as it does now, the expansion of the universe accelerates forever. Galaxies beyond local groups slip away permanently. Eventually, even the merged descendants of the Milky Way drift alone, isolated in an ocean of blackness with no other galaxies visible. Future observers, if any exist, might conclude that their island of stars is the entire universe, unaware of the vast cosmic web that once connected trillions of galaxies across billions of light-years. And then even that island fades, Heat death is not a fiery ending. It is the gradual arrival at maximum entropy, a state in which energy is evenly distributed and no useful work can be extracted. Differences in temperature are what allow processes to occur. Stars shine because their cores are hotter than surrounding space. Life functions because energy flows from warm to cool. When everything reaches equilibrium, when no region is meaningfully hotter or colder than another, change slows towards stillness. Matter may decay if protons are unstable, dissolving over inconceivable spans of time into lighter particles and radiation. Structures unravel. Atoms themselves may not last forever. In that scenario, the universe becomes a thin bath of low-energy particles and photons, stretched across ever-expanding space. No explosions, no collapse, just a steady smoothing out until nothing stands out against anything else. Entropy reaches its quiet maximum. Yet this is only one possibility. Some cosmological models imagine a different fate. If dark energy were to weaken or reverse, gravity might one day halt expansion and pull everything back inward in a big crunch. Galaxies would begin to approach one another again. Background radiation would grow hotter as space contracts. The cosmos would compress toward density and heat, perhaps ending in a state not unlike its beginning. Other theories suggest a big bounce, where contraction does not end in final collapse but rebounds into a new expansion. In such a picture, what we call the Big Bang might have been a transition, not an absolute origin. Endings become beginnings. The universe inhales and exhales across cycles beyond counting. There are also ideas of a multiverse, where our observable universe is one bubble among many, born from fluctuations during cosmic inflation. In that vast landscape, new universes may continue forming even as older ones fade. Each bubble could carry its own physical constants, its own history of stars, perhaps its own forms of awareness. We do not yet know which of these paths reality will follow. The equations allow several possibilities. Observations continue to refine the options. But from where you are tonight, lying beneath a sky still lit by stars, all of those futures are distant beyond imagination. What matters in this moment is simpler. The universe, whether it ends in silence, collapse, or renewal, has already done something extraordinary. From quantum fluctuations smaller than atoms, it built galaxies. From hydrogen forged in the first minutes after the Big Bang, it created carbon, oxygen, iron. From those elements, it formed planets. And on at least one of those planets, it formed you. And here is the quiet center of it all. Whatever the distant fate of the cosmos, you are part of a universe that became complex enough to notice itself. For nearly 13.8 billion years, matter followed simple rules. Gravity gathered gas into stars. Stars fused light elements into heavier ones. Supernovae scattered those elements into space. Galaxies merged, rotated, drifted. For most of that time, there was no awareness, no reflection, no thought. Just motion, just physics unfolding in silence. And yet, from that steady unfolding, consciousness emerged. Not as something separate from the universe, but as a process within it. The calcium in your bones was forged in ancient stellar cores. The iron in your blood was born in explosions powerful enough to outshine galaxies. The oxygen you breathe was fused in stars that died before the sun ever formed. You are not merely in the universe. You are a configuration of it, a temporary pattern of atoms that can look up at the sky and wonder how it all began and how it might end. Even now, while you rest, expansion continues. For every megaparsec of distance, space grows by about 70 kilometers each second. Galaxies gently recede from one another. The cosmic microwave background cools fraction by fraction. Dark energy quietly shapes the large-scale destiny of everything. None of this demands urgency. The universe does not hurry. It has never rushed from one era to the next. Hundreds of millions of years passed before the first stars ignited. Billions more before complex life appeared on Earth. Trillions will pass before the last red dwarfs fade. The timeline of the cosmos is measured in spans so immense that a human lifetime is almost invisible against it. And yet, that does not make your life meaningless. It makes it rare. We live in what might be called the stellar springtime. Star formation has slowed from its peak billions of years ago, but it has not ceased. The night sky still holds galaxies by the trillions within the observable universe. Black holes still merge. New planetary systems still form in cold molecular clouds. This era, bright and structured and dynamic, will not last forever. There will come a time when future observers, if any remain, see only a darkened sky inside a single gravitationally bound remnant of what was once many galaxies. But tonight is not that night. Tonight, there are still stars overhead. Tonight, the universe is still rich with gradients, contrasts, warmth and cold, light and shadow. Entropy has not yet reached its maximum. There is still energy flowing from hot to cool, from core to surface, from star to space. That flow is what allows complexity. It is what allows breath, thought, memory. In the far future, when equilibrium approaches and differences vanish, processes will slow beyond recognition. But you exist now, in an era where differences remain, where light travels across millions of years to reach your eyes, where galaxies cluster along invisible filaments of dark matter, where the cosmic web still holds intricate structure across billions of light years. It is easy to feel small when considering trillions of years and unimaginable distances. But small does not mean insignificant. A single fluctuation in the early universe, smaller than an atom, became the seed of a galaxy. Tiny variations, amplified by expansion and gravity, shaped everything that followed. The large-scale structure of the cosmos grew from subtle imbalances. In a similar way, small moments accumulate. A single thought leads to another. A quiet night leads to reflection. The universe does not require you to solve its mysteries tonight. It does not ask you to carry the weight of its future. Its expansion proceeds whether you are awake or asleep. Dark energy continues its quiet work. Black holes continue their slow evaporation over spans so long they defy imagination. Stars continue burning in distant galaxies. All of it unfolds according to laws written into the fabric of space-time. And here you are, a brief luminous pattern within that fabric. The universe may one day reach heat death, a state of near-uniform temperature and maximum entropy. Or it may collapse and bounce, beginning anew. Or it may be one bubble among countless others, part of a multiverse beyond our horizon. We do not yet know. Uncertainty is woven into cosmology. The equations guide us, but they do not yet close the story. What we do know is that the cosmos has already transformed quantum whispers into galaxies, and stardust into awareness. In you, the universe has a moment of self-recognition. That is not permanent. Nothing in physics suggests it will last forever. But permanence is not required for meaning. A star shines for billions of years and then fades. Its light still mattered. A civilization may last only thousands. Its thoughts still ripple outward. A human life lasts decades. Within those decades, there can be understanding, connection, curiosity. You are part of a story that began in a hot, dense state and expanded into structure and light. You are living in a universe that, for now, still glows. If you are still listening beneath the stars, gently type 3 in the comments. Let it be a quiet signal, a small acknowledgement that you are here, awake within the vastness. And as you breathe, remember that nothing demands urgency. Galaxies are drifting apart at 70 kilometers per second per megaparsec. And yet there is no rush. Everything unfolds in time. Let the scale of it soften your thoughts. Let the future trillions of years rest where they belong, far beyond tonight. The vastness is not something to fear. It is something to float in. If we continue drifting even farther forward, beyond the evaporation of the last black holes, beyond the cooling of the final embers, we arrive at a universe almost unimaginable in its stillness. The background radiation, once a faint microwave glow at a few degrees above absolute zero, will have stretched to wavelengths so long they barely carry energy at all. Space will be thin beyond comprehension. Particles, if protons are unstable, may have long since decayed into lighter remnants. What remains could be a sparse sea of photons, electrons, positrons, neutrinos, each separated by distances so immense that interaction becomes nearly impossible. Without temperature differences, without density gradients, without gravitational structures, change slows to a near halt. Not because time stops, but because there is almost nothing left to happen. Entropy has done its work. Energy is evenly distributed. The cosmos becomes a vast, dark equilibrium. And yet, even in this vision, there is something strangely gentle about the ending. There is no final crash, no cosmic scream, just a gradual thinning, a smoothing out of all contrasts. The same laws that allowed stars to ignite and galaxies to form also allow energy to disperse and structure to dissolve. The universe does not betray its rules at the end. It simply follows them. Some physicists have wondered whether quantum fluctuations could still occur in such a thin future. Even in near-empty space, quantum fields never become perfectly silent. Tiny fluctuations might still ripple through the vacuum. Given timescales so immense they erase intuition, rare events could happen. A fluctuation might momentarily concentrate energy in a small region. Perhaps, in some speculative scenarios, conditions might resemble those that once triggered inflation. From such a fluctuation, a new expanding region of spacetime could bud off, forming what appears, from its inside, to be a brand new universe. In that case, endings and beginnings blur together. Our cosmos could be one chapter in a much longer narrative, where universes give rise to other universes through mechanisms we only partially understand. Or perhaps not. Perhaps the far future remains quiet forever, an asymptotic drift toward colder and colder emptiness. Both possibilities remain within the realm of theoretical physics. We test what we can. We measure the cosmic microwave background. We observe distant supernovae to track the rate of expansion. We listen for gravitational waves from merging black holes. From these clues, we reconstruct both the past and the likely future. But there are limits. Our observable universe is finite because light has had only 13.8 billion years to travel. Beyond that horizon, there may be more structure, more galaxies, perhaps entirely different conditions. We cannot yet see them. We live inside a cosmic bubble of visibility. Within that bubble, the story is already astonishing. From a uniform plasma emerged galaxies arranged in a vast web stretching across billions of light-years. Roughly 5% of the universe is ordinary matter, the kind that forms stars, planets, and people. About 27% is dark matter, shaping galaxies through gravity while remaining invisible to our instruments. Nearly 68% is dark energy, driving accelerated expansion. These proportions mean that most of reality is not directly seen. And still, from that mostly invisible framework, luminous structures arose. The future, whether heat-death, crunch, bounce, or multiverse branching, does not erase that achievement. The fact that the universe once burned with stars and now holds minds capable of tracing its history is already extraordinary. When you think about trillions of years, it is easy to feel as though everything now is fleeting. But fleeting is not the same as trivial. A mayfly lives for a day, yet its life is complete within that day. A red dwarf may live for trillions of years, yet its story also ends. Duration alone does not define significance. What matters is that patterns arise, persist for a time, and then transform. The atoms in your body were assembled on Earth only recently compared to the age of the cosmos. Before that, they traveled through interstellar space, part of gas clouds, part of earlier stars. In the future, they will disperse again. Matter is recycled on cosmic scales. Consciousness, as far as we know, is rarer. It requires particular conditions: stable energy flows, chemical complexity, time for evolution. Those conditions exist now. They may not exist forever. That makes the present era quietly precious. As you rest tonight, you are doing something the early universe could not do. You are aware of expansion, aware of entropy, aware of the possible fates that lie trillions of years ahead. The universe may cool toward equilibrium, but at this moment, it is far from it. Stars still shine. Galaxies still cluster. Black holes still merge. sending ripples through space-time that we can detect across billions of light years. The cosmic story is ongoing. Nothing demands that you solve it. Nothing requires that you hold all its scales in your mind at once. The expansion rate of about 70 kilometers per second per megaparsec continues whether you think about it or not. Dark energy does not accelerate more quickly because you are anxious. Gravity does not weaken because you are tired. The cosmos unfolds with or without your attention. That is part of its comfort. You are free to rest inside it. The far future may be an endless dark ocean, but tonight there is still light. Let that be enough for now. And so we arrive at the gentlest horizon we can imagine. Not a wall, not a final curtain, just a gradual thinning of light and difference, stretched across spans of time so vast they make the present feel like a warm spark in an endless night. The far future of the universe, whether it ends in heat death, collapse, rebirth, or branching into new cosmic bubbles, does not rush toward us. It unfolds slowly, patiently, almost tenderly. Trillions upon trillions of years will pass before the last red dwarfs fade. Quadrillions before black dwarfs dominate the dark. Timescales like 10 to the 67th power years before even stellar mass black holes evaporate. These numbers are not meant to alarm you. They are meant to calm you. They are so large that nothing you do tonight can hurry them or delay them. The universe is not fragile in that way. It does not teeter on the edge of tomorrow. If heat death is the final chapter, it will not come with violence. It will be the ultimate equilibrium, a state where temperature differences vanish, where no region is meaningfully warmer than another, where no free energy remains to power stars or life. Entropy will have reached its quiet maximum, every gradient smoothed, every imbalance resolved. It sounds bleak when described in simple terms, but there is also something serene about it. The same physical laws that allowed galaxies to ignite with light will gently guide them toward stillness. The cosmos will not shatter. It will rest. If instead expansion reverses and a big crunch gathers galaxies back together, that too would be part of the same consistent physics. Space would contract. Background radiation would grow hotter. Structures would compress toward density and fire. And perhaps, in some models, a new expansion would follow. A big bounce. A renewal. In such a universe, endings are not annihilations but transitions. A cosmic heartbeat, expanding and contracting across unimaginable eras. We do not yet know which scenario reflects reality. Observations suggest accelerated expansion continues, driven by dark energy. But the nature of dark energy remains one of the deepest mysteries in physics. It may remain constant. It may change. It may one day transform the destiny of everything. And beyond these possibilities lies another idea, that our observable universe is only one region within a much larger multiverse. During inflation, tiny quantum fluctuations may have caused space to expand unevenly, creating separate domains that evolve independently. In that case, even if our universe cools towards stillness, others may be forming elsewhere, each with their own constants, their own stars, perhaps their own moments of awareness. We cannot yet test this directly, but the mathematics allows room for such vastness. Through all these possibilities, one truth remains steady. You are part of a cosmos that once turned simplicity into complexity. The early universe was nearly uniform, a hot plasma glowing with light. Tiny fluctuations, 1 part in 100,000, seeded the galaxies. Gravity sculpted filaments and voids across billions of light years. Stars forged heavier elements in their cores. Supernovae scattered those elements across space. Planets condensed from dust. On at least one of those planets, chemistry became biology. Biology became consciousness. The universe became aware. You are that awareness, not separate from the cosmos, but a temporary luminous pattern within it. The universe may be 13.8 billion years old, yet in you it reflects on its own age. It may stretch across billions of light years, yet in your thoughts it compresses into meaning. Even the expansion rate, about 70 kilometers per second per megaparsec, can be held quietly in the mind. For every 3 million light-years of distance, space grows by 70 kilometers each second. Galaxies gently recede, not because they are racing through space, but because space itself stretches. And while that stretching continues, you breathe in and out. Nothing in this vastness demands urgency. The stars will not burn out tonight. Dark energy will not suddenly accelerate because you are awake. Black holes will not evaporate before morning. The far future, with its black dwarfs and fading radiation, lies beyond comprehension, beyond the lifespan of civilizations, beyond even the endurance of galaxies. You do not need to carry it. What you can carry is the quiet recognition that you exist in a rare and luminous era. A time when stars still shine, when galaxies are still visible beyond our local group, when the cosmic microwave background still glows faintly at 2.7 Kelvin. A time when entropy has not yet flattened all difference, when gradients still power thought and life. You are here during the bright middle chapters of a cosmic story. So as you lie in the dark, let the scale of trillions of years soften whatever feels urgent. Let the image of galaxies drifting apart ease whatever feels tight. The universe has already endured nearly 14 billion years. It will endure far more. Your role tonight is simple: to rest, to breathe, to be a small, conscious ripple in a vast, expanding sea. If you are still listening beneath the stars, gently type 3 in the comments. Not as a demand, but as a quiet signal. A way of saying, I am here. I am aware. I am part of this immense unfolding. And now, let the vastness cradle you. Let the future trillions of years drift far beyond your thoughts. Everything unfolds in time. And for this moment, you are exactly where you need to be.